Good morning to everyone. In today's video, we are going to see the relations for star connected load. Already in our previous classes, we just come across with how the line and phase quantities are there in the star connected as well as delta connected mode, delta connected connections. So today we just concentrate about the star relations in our star connected mode. So this is the star connected load within a supply R by B. So kindly observe this one. Kindly observe this one. We have the supply R by B. The currents flown through these lines, the currents flown through these supply lines, currents flown through these supply lines, we call it as a line current. The current flowing through the supply lines, we call it as line current, which is nothing but IR, IY and IB. These are the line currents. And the voltages across these lines, we call it as line voltages. So we are considering in a clockwise direction as per your phasor diagram, RY, YB and BR. Okay. So RY is nothing but VR, and the voltage across your Y and B connection is VYB, and the voltage across your B and R is VBR. Okay, these are the line voltages. We have the idea about line currents as well as line voltages. Now this is your load, this is the load. We are considering it as a balanced load. That's why instead of considering ZR, ZY and ZB, we are considering the impedance value as Z phase, which is equal in all the phases. At the same time, the current flowing through each phase, that means the current flowing through each phase, we call it as a phase current. So if you observe this is the current flowing through this R phase, we are assuming it as IR, and current flowing through the Y phase IY, and current flowing through this B phase is IB. And same fashion, what is the voltage appearing across the R phase? We are considering it as VR, voltage across R phase. Similar fashion, VY and VB. And these voltages are called phase voltages, and these are the phase currents. If you observe this, all the phases, all the impedances are connected at a point that is neutral. Okay, that is the neutral. With reference to this, from R to N, we call it as an R phase, Y to N we call it as an Y phase, and B to N we call it as an B phase. The terminal, ending terminal, we consider that. Okay, the same points we are written here. You may call this one as VR or VRN. So the potential between 2 points we need to mention VRN or VR. Both are correct, because neutral we are considering it as ground 0 volts. So for time being you may mention or may not, there is no issue. Okay, the same points I mentioned, it is the line voltages are which is represented as VL, nothing but VRY, VYB and VBR, and the line currents IL represented as IR, IY, IB, and the phase voltages we represent as VR, VY and VB, and the phase currents we represent it as IR, IY and IB. If you observe these things, the line currents and phase currents are same in the star connected mode. So with this we draw one conclusion that the line currents are same as your phase currents in star connection. It is same as in your star connection, that is IL equals to I phase. Now we are switching for the voltages. Now I am considering one phase between two terminals, that is RY, R and Y phases. Between these two phases, the voltage is VRY. The voltage between these two phases is VRY. If these terminals, if I am extending from supply to load, it will be appears between these two terminals. So I'm just considering the terminals R and Y in supply side. The voltage is VRY. If these terminals, if I am extending towards the supply, towards the load, these two are the terminals. What is the combination? The voltage between the terminals V and the voltage between the terminals R and N, the voltage between the terminals R and N, as well as the voltage between your terminals N and Y. Okay, N and Y. Now that means the voltage between R and N and the voltage between N and Y. So kindly remember, the voltages whatever we are adding, it is in phasor addition. It should have both direction as well as magnitude. It is having both direction as well as magnitude. But the current is flowing from Y terminal to N terminal. We are not having any current flow from the N to Y because the higher potential is Y. Okay, always current tends to flow higher potential to lower potential. How we considering that water always flows to the downward direction. Similar fashion, always current flows from higher potential to lower potential. So this will not be existing. So to convert this one phasor from lower potential to higher potential, that means if I am having any phasor, which is the direction of 5 angle 0. Okay, if I am having the direction of phasor 5 angle 0, if I want to modify the current direction, without changing any magnitude, okay, if I want to convert this one from this to this, the only thing is we need to modify the sign of the phasor. Instead of considering the positive, we will considering it as negative. That means we are changing the direction. Similar fashion, instead of considering the VNY, we are modifying it as minus VYN. So the same things we are written here. So VRY phasor, we represented it as VRN plus VNY. But to modify the direction, because this is not available for us, for that we just modify the direction by changing the sign of your magnitude. So it will be represented as VRN minus VYN. So neutral terminal, you may not no need to represent. So VRY will be written as VR minus VY. Similar fashion, if you want to find out what will be the voltage, between your Y and B terminals, you kindly go into this across these terminals. That means VY, VYN plus VNB. So to modify this, we need to change the direction. So VY minus VB. Similar fashion, VB, VR, VB and VR. So VBN plus VRN. So VNR. So to change the direction, we just go for VB minus VR. Okay. So this is the phase how we written the equations. So we write the equations in terms of phase voltages and line voltages. Already we know these are the values. These are the line voltages and phase voltages. Now we have the relations in between the line and phase voltages. Try to draw the phasor diagram. And here, with the previous knowledge, the phase voltages are aparted by 120 degrees. This one we already know. So with that knowledge, we draw the phasor diagram. So initially I draw the three phasors, okay, three phasors, okay, phase voltages similar to our standard notation. So we just simply drawn VR, Vy and Vb, and each one are aparted with 120 degrees. Each one are aparted with 120 degrees. So this is our basic diagram. For this basic diagram, from phase voltage to line voltage, if I want to modify, so I'm just considering this one. I have VR and I have Vy. Kindly remember, we have the vector, phasor addition. We have only the phasor addition. Phasor subtraction is not available for us. For this reason, this can be written as VR phasor plus minus of Vy. Instead of subtracting, we are just adding two phasors. By considering other phasor as negative of your Vy. Okay, negative of your Vy. So to considering negative of Vy, already what I said previously, we need to consider the direction as opposite. Similar fashion right now. So if this is 5 angle 0 degrees, if I want to have the opposite direction, or if I require minus 5, what should I do? I just change the direction. Same thing here I'm doing. I have Vy, I need minus Vy, so I'm just changing the direction. Instead of flowing this side, I'm just considering this side. So kindly consider these two are in straight line, that is it making the angle of 180 degrees. It is making the angle of 180 degrees. So up to this point, that means up to this point from VR to Vy, it is having around 120 degrees. Completely Vy to minus Vy, it is 180 degrees. That means minus Vy to VR, we are having rest of the 60 degrees, because 60 plus 120, the total 180 degrees is completed. So the angle between your VR and minus Vy is nothing but 60 degrees. So minus Vy leads VR by 60 degrees. Now by using your parallelogram law from your 8th class, if you want to add two phases, we just draw the parallel lines of your phases. So for this VR phasor, we are considering this is the parallel line, and for this one we are considering these two parallel line. So the diagonal which is passing through these lines, are nothing but your resultant, and this resultant cuts the angle. Bisects the angle exactly half of the value. So for that, I am considering the triangles O as an origin, and A is your VR vector. So OA vector represents the VR phasor, and the same time your OB vector represents the addition of VR and minus Vy. That means VR and minus Vy addition vector is nothing but VRY, nothing but your line voltage, So this is your phase voltages. These are your phase voltages. Vy, minus Vy and VR is your phase voltages. So I think up to this point it is clear. So these are your VR minus Vy, the resultant vector VRY, which is the line phase, and the angle between your line voltage and phase voltage is 30 degrees. Now draw a perpendicular on the line voltage. on the line voltage from your point A. So from this point A, we draw the perpendicular on line voltage OB. So now this point C bisects, that means this perpendicular bisects this vector exactly half of the value. That means this is OC and BC. So OC and OB is nothing, OC and BC is nothing but OB by 2. OB by 2, nothing but your VL divided by 2. VL divided by 2. So now consider the cosine of your triangle OAC. Consider the cosine of your OAC. So it is nothing but this is the opposite to your hypotenuse, opposite to your 90 degrees. This is the hypotenuse, adjacent side and opposite side. So cos 30 degrees equals to OC divided by OA. OC, how we mention, it is half of your line voltage value. So OC equals to VRY divided by 2, and OA is nothing but your VR. So cos 30 value is root 3 by 2. So VRY is line voltage, and VR is your phase voltage. So from this, if you cancel over 2, so V phase is VL equals to root 3 times of V phase. So with this, in the star connection, the relation between line voltages and phase voltages, we are given it as VL equals to root 3 V phase. In star connection. This is the relation line voltage and phase voltages. Now power in the circuit. For the single phase power AC, we given it as, that means the real power. Already we come across with different types of powers. Right now I am talking about the real power. Real power as applied voltage into active component of your current, that is nothing but P equals to V into I cos phi. Now I am considering only single phase, but we require for 3 phases. For 3 phase, each phase individually we have the powers. So power in the circuit is nothing but 3 phase power. So 3 into V phase into I phase cos phi. We have the relation with the phase and line quantities. So V phase equals to VL divided by root 3, and phase voltage, phase currents and line currents are equal, so it will be IL. So with this, the power will be equals to root 3 times of line voltage and current voltage of active component. Okay, active component of line current. So this is for relation of star connected load. So this is our tutorial question. Kindly observe this. You need to draw the complete phasor diagram of a 3-phase star connected inductive load connected across 3-phase AC supply. So now if you observe this, I just mentioned this is the load Z phase. Okay, I'm just mentioning this load as Z phase, but I didn't disclose whether it is an inductive load or capacitive load or resistive load. If you know the relation between what is the phase difference between voltage and current in a particular load. That means if I am considering it as a resistive load, the phase difference between voltage and current is in phase. Whether if I go for an inductive load, the voltage and current relation is lagging. Similarly, if I go for the capacitor, it should be a leading one. Okay, so now they ask the complete phasor diagram for a 3-phase star load, 3-phase star connected inductive load. If I draw this, it should be just a three-phase star connected load phasor diagram. That means it is not giving which type of load, especially it is not an inductive or not a capacitive. I'm not at all considering the currents here. So now I need to draw the phasor diagram. So for one phase I'm drawing. You can interpret for the other phases also. It will be nice. So same thing, I'm just draw the three phases, and kindly consider these are the all balanced ones. All are balanced ones. Okay, this is VR, this is VY, and this is VB. Now due to the inductive load, the current is lagging. The current is lagging by angle phi. So the current is lagging by an angle phi. This is IR. This is IY. I'm not considering the whatever the phase difference, not higher values. This is IB. So these two have the phase difference of phi. Kindly remember, this is your phasor values, I phase and V phase, phase voltages and phase currents. Now with this I need to extend, because as we know this, we need to draw the vector. So if I try to draw the vector, the vector will be this one. The vector will be this one, which is having the value of minus Vy. For these two things, I need to draw the resultant vector. So the resultant vector is this one. So the resultant vector, which is nothing but V R Y. Up to this, the same notations. This is 60 degrees. This is, up to this it is 60 degrees. VR and VY, it is having 60 degrees, and the resultant will cut it by 30 degrees. With this we can draw some conclusions. As I phase, okay, whatever the phase current lags V phasor, that means phase voltage, by an angle of phi, in each and every phase. So in every phase it is having the lagging load, inductive load. Okay, at the same time whatever this line voltage leads your phase voltage by angle of 30 degrees in each and every phase. I just draw for one phase. You can try to interpret for the rest of the phases. So here you can draw for Y and B, and here you can draw for R and B. So the final thing I just represent to you. I just pause the video. So here these blue color lines represents your the phase voltages, and the black color lines represents your line voltages. So I hope the relation between your voltages, currents, and power in your star connection load you may understand with this video. I hope. Thank you.